Hey everyone, today we are going to finally start deep reinforcement learning, namely the DQ learning algorithm. Now, if this is your first foray into deep reinforcement learning, I would highly recommend you stop. I know DQ learning sounds sexy, we're going to throw neural networks into reinforcement learning, but it's not a good place to start. You should definitely be comfortable with more traditional reinforcement learning methods, like all the stuff that we've covered earlier. We covered the Bellman equation, Bellman optimality equation, where does all this stuff come from? We covered the different model-based methods like policy iteration and value iteration when you have the MDP available to you. When you don't have the MDP, then we covered all of these different estimation methods like Monte Carlo. We covered TD methods like SARSA and Q-learning, and then some alternative variants of the TD methods like n-step TD estimates and TD lambda. So if you are not comfortable, especially with Q-learning, kind of all the ideas that go into standard TD learning, like on policy, SARSA, or off policy, like Q-learning, I would highly recommend not to start here and go back, get comfortable and familiar with those topics first, and then come back here, because then this will all make a lot more sense. But just as a really quick recap of Q-learning, what was Q-learning? The idea behind Q-learning is I want to update my Q table in the direction of my TD target. So my TD target in the case of Q-learning was this off-policy variant where we want to use the reward I got for taking a specific action at a state plus discounted future rewards. And the thing about Monte Carlo is we had true future reward data because we played a full game. But the benefit of Q-learning is we could update our game as we played, update our model as we played the game, which is really neat, but it required us to do bootstrapping. We used our current estimate to update our estimate, right? It's a little bit different, but it allows us to update our game or update our model as we're playing the game. So this is the standard TD target for off-policy Q-learning, right? Off-policy Q-learning, where you're taking the max of the Q for the next state, whatever action give me the maximum Q value. Now, of course, we could also do on-policy like SARSA, where we do, instead of the max action, pick the Q value of the actual action we took. And SARSA and Q-learning both have their pros and cons, and I cover all of that in those previous videos. But the main idea is we want to update our Q values in the direction of the TD targets. We have our current estimate of the Q values. We have our TD target, which is some information, some return information I got from the game. And I want to minimize the distance between these two by updating my Q values in the direction of those TD targets. Now, here's some limitations of the Q-learning method. We started with the Q table, right? The Q table is just initialized as zeros, and we're hoping to iteratively, using this formula right here, iteratively update my Q values. And the Q values, again, is what tells me what is the best action to take at a specific state. And I want to iteratively update all of these to find those Q values until they converge. The problem is this. Well, in our standard game that we looked at, like the frozen lake game where we have these discrete states, it was pretty easy, right? You're either at this state or this state or this state, and at every state you could go left, down, up, down, left, right, right? So those are your options. But what if our states are a little bit more complicated? Complication number one, continuous states. What if every state isn't defined by a one hot encoded vector of where am I, like here in the frozen lake game, but rather they're defined by angles, right? Some continuous number. You could think angle, you could think anything else, but you could describe a bunch of different states using continuous numbers. This would be a little bit more challenging to deal with in a Q table, which typically expects discrete state values, right? Discrete states that you can be in. Also, what if you have multiple features? So the game we'll be mostly working with is this LunarLander game. And what if each state is defined by a set of features, not just one feature of just where am I or just what is the angle, but rather a bunch of features. Where am I, x and y position? And these are continuous values. We have our x and y velocity. How fast am I moving in the x and y direction? What is my angle? What is my angular velocity? And then we have these Boolean values of left and right leg contact. Is my left leg touching the ground? And is my right leg touching the ground? Which means each state is defined by a bunch of different features, right? So we have a feature vector representing every state. We could technically maybe set up a Q table like this, but it would be very large and very sparse and honestly very difficult to update in a meaningful way. And so this is why Q-learning, standard Q-learning using a Q table may not be best for these types of situations. And so instead, we can leverage something else. Why not a neural network? So how does a neural network fit into all of this? A Q table is something that takes in a state and tells me the Q value at different actions. But what if I had a neural network do exactly that? I can pass in a state vector. The state vector in the case of Frozen Lake would be one hot encoded. It's 0 for the states I'm not at and 1 at the state that I'm at. So you'd have a one hot encode vector. Or if we have these kind of more complex things where we have a bunch of different features, well, this is my feature vector, right? So I have a bunch of input feature vectors. And then on the other side is the actions that I can take, right? Action 1, 2, 3, 4. And my neural network's goal is to predict the Q value of the different actions given this input state vector. And so that's the key idea of why we could potentially use neural networks rather than a Q table to solve the same problem. And neural networks are much more flexible because we can pass in continuous features and we can pass in many of them, and it's no problem, right? It's not like the compute cost will be significantly higher. On the other hand, in Q tables, this will scale poorly if our if our input features become continuous, then we have to somehow discretize them and you'll have lots and lots of different possible states. And then if you have multiple combinations of features, you'll have a multiplicatively increasing number of states here for all the different possible combinations of those multi-feature vectors. And so this is exactly why Q networks for deep Q learning will be awesome. Now, of course, if we're doing a neural network, there are a couple of extra caveats that we have to think about. Number one caveat is we typically train neural networks in batches. How does that exactly work here? In Q learning, we just took a step, computed our TD target, update our model, update our Q table, then take another step, compute a new 2D target, update our Q values over and over and over again, right? As we play the game. It's just neural networks, we don't update with one piece of data. We typically train with batches of data. And so this leads to something called the replay buffer, which we'll be calling the time capsule, but same idea, the replay buffer. And the replay buffer is, imagine it's just a collection of reward or a collection of experiences. You're playing the game, you're doing things. And as we play the game, we're going to collect these experience tuples, right? We're going to have a state, what action did I take, what reward did I get, what state did I end up in, and is the game over? And we're going to collect these as we go. And so what we can do is why not go ahead and just store these in some type of a container. Store them and then randomly sample batches of information, batches of experiences to train on from that time capsule. And so that's the main extra thing that we're going to have to implement is this time capsule. Go ahead and store up a bunch of these experiences and then random sample from them. There's a couple of extra details there that we'll talk about when we actually implement it, so we'll see it when we get there. The other thing we need for a neural network is a loss function. What do we want to minimize here? Well, let's take a look at this again. Our Q value, what we're doing is updating our Q value in the direction of the TD target. We're finding the difference between my TD target, the return that I computed from the state, what's my current estimate of the Q value, and then I subtract them and I update the Q table in that direction. So really, all we're trying to do is minimize the distance between the TD target and the Q values. And if that's the case, then can't I just use like mean squared error or L1 error like you see here, or we could do Huber or really anything else. You can come up with a bunch of different metrics, but mean squared error kind of just makes sense here. I want my predictions, my Q predictions, to predict the TD targets. And so why not train a neural network to do that by minimizing the mean squared error distance between my predictions and my targets. And so this is what we'll essentially be implementing as we go. So let's just go ahead and get started here. So I've already done a couple of little things here just so I don't have to type them out. Standard imports, we just have torch now on top of everything else. And this is how we can go ahead and play a game. So we can load the LunarLander game in RGB array mode so we can visualize it. The Gymnasium has this nice little wrapper called record video. So as you play the game, it will go ahead and record a video for you. And I went ahead and just visualized that video here. And here's that game happening. And you can see, of course, this model, game did not go very well because we're just random sampling our action at every single iteration, right? So there's really nothing interesting happening here. But that's the main idea. We have our model here, or our game here, and we can record it. So the API, everything here should look very familiar to what we had done for our earlier games, like the Frozen Lake. So it hasn't changed all that much. And then, of course, what are our states? Well, again, as you remember, as we saw right here, every state is defined by a set of features, not just one feature, not just where am I, but a whole set of features. And so there's 8 numbers that represent this specific state. And here those are, right? We have our X and Y coordinate we have some x direction velocity, y direction velocity, we have our angle, we have our angular velocity, and then some Boolean values that identify, are we touching the ground? Is the left leg touching the ground? Is the right leg touching the ground? And then we, of course, have our actions as well. So we can do our env.actionSpace, I believe. Yep, env.actionSpace. And there are 4 actions available to you. The 4 actions are 0 is do nothing, so this would just fall. We have 1, fire the left engine, 2, fire the main engine underneath, and then 3, fire the right engine. And you can see all of that here. So if we pause right here, you have your left engine, main engine, right engine. And so now we, of course, also have a reward system already built into the game, so we don't really have to think about this, but this reward kind of makes sense. So our rewards are, as we're further away from the landing pad, the worse the reward, right? So our goal is to land here, right? So the further we are away, the worse the reward. And then we have our how fast or slow are we moving? If we're moving too fast, that's not safe for the passengers inside the lunar lander. So of course, that would also give a worse reward. And then the more tilted our lander is, that will also penalize the reward, right? We'll have less reward, or more of a, less reward. And then every time our leg touches the ground, we get 10 points, right? So that's a good thing. But of course, our lunar lander only has so much fuel, so we don't want to just use all of it up. So every time we're using the side engines, we're going to decrease our reward by this much. So the more fuel we use, the more we end up, penalizing it. And then of course, in the same way, if we use our main engine, which uses more fuel apparently, there's a higher penalty for using it. And then we get, if we crash, we get negative 100 reward. And if we land safely, then we get plus 100. And as long as we get 200 points, that means this game is solved. And so this is essentially the main idea behind the reward function. You can see it's pretty interesting, a little bit complicated, and you could come up with your own reward function, but we'll just use the one that comes default with the game for now. So step 1, we want to replace our Q table with a neural network. It's very simple. As you can imagine, this neural network here is just a linear layer, right? Or we can just have a couple of linear layers with some nonlinearity injected into it, just like any other standard neural network. So it's going to be ni.module, def init, and there's a couple things. We have our self, we have our input state features. How many input features do we have? Well, there's 8 because we know every observation is represented by 8 numbers. So that's 8. Then we have our num actions. Well, there's 4 things we can do, right? We know what the 4 possible actions we are. Do nothing, fire left, main, fire right. And then we have our hidden size, hidden features, is 128. And that's a hyperparameter, right? How many hidden features do you want in the intermediate representation? So we have super.init, and let's just define our model. Self.fc1 is a linear layer, and the linear layer takes input state features and outputs the hidden features for the hidden layer. Then the second linear layer will be linear. It'll be our hidden features to hidden features. And self.fc3 is, again, a linear layer that's going to take those hidden features and map them to the number of actions we can take at that state. And so our forward function, self-x, we're going to do x is self.fc1x, but of course it's good to inject some nonlinearity, so we'll just use relu for now. X is, again, f.relu self.fc2x, and then lastly x is self.fc3x, which is going to go ahead and map it to the different actions. And this is our neural network, and that's it. And from what I remember, this is essentially the neural network we're going to be using for almost every future implementation we'll do, because the neural network part of reinforcement learning, at least for now, is the least interesting part. This is essentially what we're going to use to solve this environment over and over again. We're just going to do them in a bunch of different ways, and we'll see what that looks like as we get into more advanced models. For now, though, this should be more than sufficient to solve a relatively simple game like this. So now that we've set up our neural network, again, remember, we have to train in batches, which means we need to set up our replay buffer. And there's essentially 2 things that go into the replay buffer. I'm going to call it the time capsule. And this is going to be simply a thing that stores a bunch of memories. So it's going to be self, we have our max memories, and we have num state features. which we know is 8 in this game. Now you might be asking, why do we have max memories? Don't we just want to store as many memories as we can to sample from? And that's technically true, but there is one caveat. Our neural network is going to get better and better at playing the game. So let's say the max memories was just 5. So we have 5 slots to store memories. So we have slot 1, and we'll have 2, 3, 4, 5. So slot 2, slot 3, slot 4, slot 5. Let's say our max memories was 5. So at the beginning, when our neural network doesn't know anything, it's going to go ahead and just start playing the game and start filling these slots with memories, right? And each memory, as you remember, is this experience tuple. It's a what state was I at, what action did I take, what reward did I get, where did I end up, and is the game over? So those are my experience tuples. But as I fill them up, my neural network will also be training, getting better and better, where at some point, these memories are no longer relevant because this was from an older version of the neural network that sucked at playing the game. Which means I want to now replace these old memories with brand new memories. And this is why we have max memories. The goal is we're going to fill up our memory buffer, grab random samples from them, update our neural network. But once the memory buffer is full, we're going to go back and start replacing the oldest memories with the newest ones. And you can imagine it's just going to basically fill it up and then replace everything, fill it up again, replace everything, fill it up again, over and over again. And the standard way to do this is using the DQ data structure, but we're not going to bother doing any of that. We'll just keep it simple and just write a indexing mechanism to do it ourselves. So we'll do self.max memories is max memories, self.num state features is num state features. And the idea is very simple. So again, we have self.state memory. So what are all the things? We have our state memory, self.next state memory, self.action memory, self.reward memory, and self.terminal memory. Right? These are the 5 different things that go inside each of our experience tuples. And let's just go ahead and initialize these all as zeros, and then we'll populate them, populate the slots as we collect these memories. So we'll do torch.zeros, and we know each of our states is going to be a self.max memories by num state features. So I want to store, let's set this to 100,000, will be our default. So we're going to have 100,000 memories, and each memory has 8 features in it because that's, again, our state, right? Every state is defined by 8 different numbers. So that's all I'm going to store in here. And then our next state memory will be the same thing. And actually one good thing to do is dtype is torch.float32, right? These are going to be some continuous numbers, so we can do that. And our next state will be exactly the same thing, right? The next state. What state was I at? What state did I end up at? Then we have our action memory. The action memories is a discrete value. It's 0, 1, 2, 3, because there's only 4 possible actions that I can take. So this will just be a vector of length max memories, and each memory is a discrete value, so we can do torch.long, just like that. So long tensors. And there we go. We're just going to populate each of these slots with what action did I take, 0, 1, 2, or 3. Our reward memory is going to look very similar, but a reward is just a scalar value. So for every single reward tuple, or for every single experience tuple, I'm going to end up with some reward. It's going to be some number. So I'm going to populate that slot with the reward I got for that state that I took this action and then went to that next state. And because these are going to be some scalar value, these will be some float32 values. And then lastly, our terminal memory is the game over. After I took this action at this state, did the game end? And this will be, again, some one value, and this will just be a Boolean, right? A Boolean, it's a bool. So there we go. That's our setup. So our states are going to be 8 different values because each state in this game is defined by 8 different values. And then our action is a single index, 0 through 3, for the 4 possible actions. Our reward is going to be some real number that defines the reward we got at that specific state for taking that action at that specific state. And the terminal is going to be some Boolean, true, false, that says, is the game over or is the game not over? And so we need to write 2 methods, add memory. And when we add a memory, it's going to be, we're going to add some state, some next state, some action, some reward, some terminal. And then we also need to do access memories. right? We want to do self. We want to access batch size number of memories, and we're going to move them to some device, which by default we'll set to CPU for now. So let's write the add memory method first. So as you remember, like I mentioned, we're going to have 5 slots. So 1, 2, 3, 4, 5. But at the beginning, I don't have any memories, right? At the beginning, I have nothing. So at the beginning, I'm going to fill this slot here, and then this slot, and then this slot, and then this slot, and then this slot. But once I've filled up the full capacity of my memories, I want to replace the oldest memory with newest ones. So my next memory, my 6th memory, really will go here. The 6th memory will go here. The 7th one will go here. The 8th one will go here. The 9th one will go here. The 10th one will go here. And then again, the 11th will go here. The 12th, 13th, ... So we're going to keep replacing the oldest memories with the newest ones. And again, the DQ data structure does this for you automatically, but we can do this pretty straightforward ourselves. The index that we want to be at will be self.current memories counter, which we actually have not initialized, so let's do that. Self.current memories counter is 0. Modulo self.max memories, right? Because at the beginning, this is 0 if we only had 5 memories. So if this is 0 at the beginning, then 0 mod 5 is just 0. And then 1 mod 5 is 1, 2 mod 5 is 2, 3 mod 5 is 3, 4 mod 5 is 4, right? So that gets me to the end. Index 0, 1, 2, 3, 4. But then when I go to 5, 5 mod 5 is 0. That indexes me back to the beginning. 6 mod 5 is 1. That puts me here. 7 mod 5 is 2. That puts me here. And so you can see we're essentially just restarting our indexing over from the beginning. And so this index is just that. So we have that. And so now we're going to do self.stateMemory index is going to be equal to the state, right? We're going to pass in a memory. Now each state, action, all of this stuff that's provided by the gymnasium are not tensors, they're NumPy arrays. So we just need to do a conversion. So torch.tensor, convert the state to a PyTorch tensor, and we want to make sure the dtype is identical. So dtype is self.stateMemory.dtype, just like that. And of course, we don't want to do this just once. We want to do this for all the stuff. 3, 4. Oh, I did one too many. There we go. And so we'll have our state memory. We'll have our next state memory. And we're going to pass in our next state right here with the next state memory. We'll have our action memory. We're going to pass in our action, and that'll be in that. We have our reward memory. We'll pass in our reward. And lastly, our terminal memory. We're going to pass in our terminal and terminal dtype. And that's the entire setup, right? We have essentially indexed correctly for which slot we're in, and we're just going to wrap around once we've completely filled up our memory buffer and just start from the beginning. We're going to fill those slots in at those specific indexes, and once we've filled a memory in, that means we're going to do self.current memories counter plus equals 1, just to iterate. Of course, now that we have the logic to add memory, we also need the logic to access a batch size number of memories. So let's do that. So we're going to do total memories. So this is an important step. If we want to access a batch size number of memories, we actually need to make sure we have a batch size number of memories in our thing. So if we want a batch size of 100, but I only have 7 memories in here, that's not valid. We can't do that. So we just need to verify that. So this is going to be min. How many memories do we have in total? It's going to be self.current memories counter, and then self.max memories. So what are we doing here? At the beginning, this is 0. So the min of 0 and 100,000, as we have up here, 0 and 100,000, will just be 0. So we don't have enough samples in here yet to sample from. But once this becomes bigger than batch size, so if my batch size is 100 and my current memories counter is 101, we're good to go. We can start sampling. And then once I've completely populated my max memories, well, then it's always going to have 100,000 memories. We're just going to start shuffling old memories for new ones. So the total memory is essentially just always maxed out by the number of max memories. And the minimum number of memories we start with is just whatever the current memories counter is. So we have everything we need here. And so if our total memories is less than our batch size, which will happen at the beginning of training, then we're just going to return none. Right? We don't really have anything to return yet. Otherwise, we can go ahead and random sample. So we're going to do rand sample index is going to be np.random.choice. And what we're going to do is np.arange total memories. So let's say we have 500 memories in here. We're going to create a index from 0 to 500. And then we're going to randomly select size equals batch size, number of indexes from that 0 to 500, or 0 to 499 for the 500 possibilities. And we're going to randomly sample 500 indexes from our batch. Now that we've done that, we also need to make sure we do replace equals false. We don't want to sample the same memory twice. We only want to sample it once. So that goes ahead and grabs them. After that, we'll have rand sample index. This is a numpy array, so we're going to convert it to a tensor. Torch.tensor. And we're going to do rand sample index. And dtype is torch.long. So this is me grabbing a random batch of indexes from my total memories and then converting that to a tensor. And of course, now I need to actually grab that batch, and that's easy enough to just do like this. I'll just paste this in so I don't have to type it out. Basically, our batch is going to be states. From our state memories, grab those indexes. From our next state memories, grab those indexes. From those actions, grab those indexes, just so we have the corresponding ones for each one, right? So this essentially sets up, we have the experience tuples for all those randomly sampled things. And we're going to move everything to the GPU, or whatever device we set here, so we can train on them. And this is the main new thing we needed to add specifically for our training purposes of a neural network. We can't just update on one step because neural networks won't optimize well on just one step. Computing gradients on just one sample at a time would be way too noisy. So to help the neural network train, we need to sample batches of experience tuples. And this is exactly how we can do that. Very simple time capsule method. Now that we have that, we need to build the agent, right? And the agent is essentially what's going to be doing all of the heavy lifting of setting up our model, setting up the loss function, grabbing a action to take, updating our model, everything. So we just need to set it up all right here. So we're going to do class agent, and this agent's going to take a bunch of information. So I'm just going to paste all of this in. Because this is all stuff we should already know. So we have our max memories. So how many memories do we want to store in our time capsule? Discount factor hasn't changed, right? We still will be doing our standard, right? Nothing much is changing from Q-learning. To compute our TD target, we still have our gamma discount factor. So we still need that. So we have our discount factor. We have a learning rate. This is for our neural network, has some learning rate to train with. We have our input features, num actions, hidden features. So we defined all that in the DQN model above. We have our epsilon and epsilon decay. So this is a little bit different, but same idea. We want to make sure we have our exploration versus exploitation. And it seems like for neural networks, it seems to work out quite well if we start with completely random. So if epsilon is 1, that means we're always going to randomly select our action, just so the neural network or our agent can explore the game, right? To collect experience tuples that are kind of random, trying all sorts of different things to give us some random data. But then as our model is getting better and better, we want to stop completely randomly selecting something and rather follow the policy, right? Follow our neural network. What does our neural network say to do, rather than just randomly selecting some action? And so we're going to decay it like this, right? So an exponential decay of the epsilon, and we'll see how that's all implemented. But of course, always having a little bit of randomness is helpful, right? It helps the model still continue to explore decisions that it may not have taken. So we're going to cap it at some minimum epsilon, just so some randomness is always there. So let's go ahead and add our model. Self.dqn is going to be the DQN model from before. Self.input feature, input state features, self.num actions, and self.hidden features, right? This is the model that we wrote just earlier with these 3 simple linear layers. We have a model. We then need an optimizer. So self.optimizer is going to be we can use the atom optimizer here, self.dqn. But there's a lot of really cool work of coming up with better optimizers for reinforcement learning specifically, but we're just going to stick to atom for now. Learning rate is going to be self.learning rate. We have our loss function, so self.loss function. And this is going to be nn.mse loss, because in the end, as we saw right here, we want to have our model, which is essentially this Q, to predict the TD target. So we want to minimize the distance between these two, which means why not use the mean squared error or L1 loss or Huber loss or any other metric that's like that. We're going to stick to mean squared error. We want to minimize the mean squared error between our predicted Q values and our TD targets that we collected from our experience tuples. Now that we have all of that, we of course need our memories as well. So self.time capsule is going to be time capsule, and this is going to self.max memories and self.input state features. And this was everything we did right here, right? Everything we did right here. Go ahead and initialize an empty time capsule that will start populating with memories. So step one, we want to be able to select an action. Def select action, self state. So at a specific state, I want to select what action should I do. So as a sanity check, if not is instance state torch.tensor. So if it's not a tensor, then we need to make sure it is a tensor. So state is equal to torch.tensor state, and then device equals self.device. That's just a sanity check in case we pass in a numpy array, so we can just convert it over. And the other thing is if state.dim is 1, which it will be, right? So each state is passed in as just a feature vector of shape 8. Of course, our neural network can't do that. We need a 1 by 8, right? We need a batch size, batch dimension, as that's what it expects. So if it's just 1, we're going to do state equals state.unsqueeze 0, right? Just a couple sanity checks. And we also want to make sure assert state.shape -1 is equal to self.input state features, because our state features, our state expects, each state is expected to be just 8 things. So we just want to make sure that's actually the case. And so now step 1, we're going to do if np.random.rand less than self.epsilon, right? So just like before in our epsilon greedy strategy, if you're less than epsilon, go ahead and just select a random action. np.random.choice self.action space. Select a random action to take at that state. Otherwise, and here's the important part, if we're not selecting a random action, then we're going to use our model to predict what action we should do. And in the case of our Q table, when we did this, we just selected the action with the maximum Q value. It's just in our case, we need to actually inference our model on this state. So to do this, we're going to set our model into evaluation mode, because we don't want, again, the train and eval shouldn't make much of a difference here because there isn't any batch normalization or anything, but good practice. So we're going to throw it into evaluation mode, and we're going to do with torch.nograd, because we are only inferencing our model here. We don't need to compute any gradients. Q for some state action pair is self.dqn state. Go ahead and inference our model for this specific state, and the action we take is going to be torch.argmax q sa, and just grab the value itself, so .item. And then once we've done that, throw the model back into training mode. Train. So this is our action selection, and we can then return action. And of course, like I mentioned, this epsilon at the beginning will be 1, so we're always going to select random actions, but as our model gets better and better, it makes sense to decay the epsilon, so we'll be sometimes actually selecting the model, and then once the epsilon's small enough, we'll most of the time be using what the model says rather than selecting some random action. And so that is our setup for selecting an action. Let's also throw in the method then to def update epsilon self, and this will be self.epsilon. We're going to replace it. It's going to be self.epsilon to the power self.epsilon decay. So we're going to keep multiplying our epsilon value over and over and over again until we get to the so it can start to exponentially decay with this exponential decay rate. Now, of course, we want our minimum to be 0.05. We don't want to have anything less than that, just to maintain some randomness all the time. So we're going to throw a max in here. Max self.min epsilon And here we go. So once our min epsilon is bigger than continuing to decay, then we're going to keep it at the min epsilon, right? We're not going to decay it anymore. And that should be it. That will go ahead and update our epsilon. We then have our inference, right? So let's just go ahead and write a inference script. This inference script will look exactly what we just did above for our select action, but that's fine. Inference, self, state, device, again, CPU. This is just when we want to actually use the model. Self.dqn is equal to self.dqn.to device in case we're inferencing on CPU. Self.dqn, again, .eval, and then all of this will kind of be the same. Let's do that. We're going to inference our model, grab our Q values, and then we're just going to, we don't really care about U because we're just inferencing here. We're going to return action. And we can get rid of U. So yeah, so this inference is exactly like what we did up here. We'll just have a separate function here for inferencing just to keep it nice and tidy. And now it is our train step. And this is the most important part, train step. Self batch size, right? So that's the batch size we're going to be sampling. So first, we need our batch. Our batch is going to be self.timecapsule, and we'll be doing access memories, right? The method we wrote, and we'll be doing batch size and then self.device, right? What device we want to move it to. So again, this is leveraging this method we wrote right here to access a random batch of memories. So this is my batch, which is again going to be this dictionary of states, next actions, or next states, actions, rewards, terminals. So this is just a dictionary of all the tensors I need for my setup. So for step one, we need to get our estimated Q values for current states. Okay, no problem, we can do that. Let's do Q estimate is going to be self.dqn, and we're going to pass in our batch states. Just like that. So we're going to pass that in, and this will compute our current guess. Right? This is our guess of what we think the Q value should be. And then what we need is rather the estimate for the specific action that we took, right? So we don't just want the Q values for everything. We want the Q value for the action that we actually ended up taking. So to do that, we can do this, right? We can do our Q, and let's make this, it's fine. Q estimate is going to be torch.gather, right? Gather Q estimate. And what we want is index equals batch actions. And we just need to add a .unsqueeze -1 just so the dimensions work out. Because again, remember, batch actions will just be a list. So we just need to make it basically a vector. So we're just adding an extra dimension there because our Q estimate is going to be a batch by actions. And then our batch actions here is basically just a list of size batch. We're going to add a extra dummy dimension right here. And then what we're saying is that these indexes here, like 0, 1, 2, whatever the action was, goes with the index right here. So we also need to provide that. We need to do dim equals -1 and then .squeeze -1. So what this actually means is, let's say our setup was like this. Let's say 0.2, let's do 1, 6, 4. Let's just let's use easy numbers. Let's say these were my Q value estimates for the first batch, for the 4 possible actions. And let's say we do a batch size of 2. So we have then 2, 7, 3, 8, whatever, right? So these are my neural network predicted these Q values for the first sample, for the first state, and then these Q values for the second state. And then what we want is the Q estimate of the actual action taken, right? Just like we always need it. So that means we want to we have the actual action taken. We have our, let's say in the first one we took action 2, and in the second one we took action 4. Well, let's say 3. So that means what I want is this Q value right here, and then this Q value right here, right? 0, 1, 2, and then 0, 1, 2, 3. So I want this value here, and torch.gather allows me to grab from this Q estimate these indexes, it's just this is a vector, so we need to add an extra dummy dimension to it that'll make it look kind of like this. Or actually, it'll make it more look like 2, 3, right? Kind of like that. We're adding an extra dummy dimension, so it becomes batch by 1. And then this dim equals -1 says that this 2 here refers to the dimension along the rows, right? Along the last dimension. So this is saying grab the second index. That's here. This thing, grab the third index. That's right here. And so that's just a simple way of doing it. Once I do that, I'll end up getting values like 6 and 8 for those, but I don't really need that this to be in that shape, so I can re-flatten this back into 6, 8, just like that. And so it's just a little bit of a roundabout way, but this gives me the estimate for the specific action that was taken. And so now it's time to take compute our TD target. So to do this, again, our TD target, so this is get estimate for specific action taken, right? So there we go. Now we have compute TD target. And this is going to be our reward we got plus gamma discount times the max A for Q next state A. Just like that. So that's our standard TD target, just as we had right here, right? It's going to be the reward plus discounted max Q value. So we're going to do that. So the way this is going to work out is we need the Q values of the next state. We need the Q values of the next state. We don't have that yet. We have the Q estimate for the current state. So to get the Q values of the next state, well, let's just inference it, right? We can get that. We can do with torch.noGrad. We can do self.DQN, throw it into evaluation mode. We're going to do Q next estimate. Let's make this uppercase Q to keep it all the same. Q next estimate is going to be equal to self.DQN batch next states, and then self.DQN dot throw it back into training mode. And now this gives me my Q values of the next state for all the different actions. Again, this is going to be batch by action, but what I want is the Q value of the maximum action. So let's go ahead and grab that. Max Q next estimate is going to be equal to torch.max, and we're going to grab the Q next estimate and dim equals -1, and this will return values of what were the max values and indexes. Where were the max values? Like what index were they at? We just need the values, right? We want the values themselves, or what was the max Q values. And so again, this is the setup. We have essentially to compute our TD target, we need the Q values of the next state. We know what the next states are because we have that in our batch, right? We stored that in our experience tuples. So go ahead and compute the Q values of all the next states. And because we're doing off policy learning, we want to grab the max Q value. If we were doing SARSA, then this would not have been the max A. It would have been for the actual next action taken, right? But we don't really have that information in our tuple because we then need it. We're doing this. Good. So now that we have our max Q next estimate, we can go ahead and compute our TD target. The TD target is going to be the batch rewards, right? It's going to be the, oh, my bad, batch rewards. It's going to be reward plus our discount factor, self.discount factor, times our max Q next estimate. And this one should have been uppercase Q, just like that. Now there is one last small caveat here that's important to keep in mind. This only works, right? The next action, what is my discounted future rewards, only works if my game is not over. If my game ended, right? If I took a, let's go here. If I took an action at a state and the game ended, so the done is true, that means there is no future returns, right? There is no future rewards. So we don't really need to care about anything that happens after. So in this case, the TD target would have been the reward plus discounted future. if the game ended already, there is no discounted future, so that should just be 0. So that is why we store this extra boolean here for terminal. Is the game over or not? And so we can multiply this by times, and we can invert batch terminal. Because our terminal is true or false, if it's true, that means it has a value. If true, right? True has a value of 1, false has a value of 0. We want, whenever batch terminal is true, as in the game is over, we want to 0 out future discounted things. So we first flip it. So that makes this, when it's true, it'll become 0. When it's false, it'll become 1. And then we'll multiply the future returns by 0 if this was true. That's the main idea. So now our TD target is just also keeping track of the fact that if the game is over or not. And our final loss, our loss, is then going to be self.loss function TD target Q estimate. And that's it. That's the main idea. So again, let's just do a really quick recap here. What we do is we grab a batch of data of experience tuples. We go ahead and compute what is my estimated Q value for the action I actually took at these states. So what I've done here, if we go back to right here, I've computed for this specific action I took at this specific state, what is the Q value? How did I do? And then I compute my actual TD target for my data. I have the next state I was at, I have the reward that I took, I have whether or not the game ended. So using all this information, I can compute the my TD target, right? Go ahead and add to the reward discounted future rewards for my Q values. So that's me computing all of that stuff. Go ahead and compute that TD target. And my goal is to make sure that the Q estimate here, Q estimate, uppercase Q, is close to the TD target. I want to minimize the mean square distance between these two. And now that I've computed a loss, just like always, we can do loss.backward optimizer dot, and it's going to be self.optimizer dot step self.optimizer dot 0 grad, right? We're going to go ahead and update the model here. And once we've taken a specific step, we're going to run self.update epsilon, right? So we're going to update our epsilon every single step that we train. And that's it, right? This is how we can update our model. So hopefully there's no bugs in here. We'll find out soon enough. So let's go ahead and write our trainer now. So this is going to be class trainer. And I'm going to, again, copy all of this stuff in because it's the same as before. So this is all the stuff. How many games do we want to play? What's the minimum reward for a successful game? So 200, like we saw, was a successful game. We have our game tolerance, right? So how many games do we have to successfully win in a row until we say, okay, model's good enough, we can stop. We have our, and then this is all the stuff from before, right? Max memories, discount factors, the learning rate we're going to learn at, our batch size, input features, all the other stuff, right? Nothing crazy. And I also want to store my running average of my rewards as I'm going, just so I can keep track of it and plot it after the fact. So let's go ahead and do this. Our tolerance, we already defined our agent above, tolerance. So our tolerance, our ending tol is 0. Basically, I want to win 10, in this case, 10 consecutive games. I want to have a successful plus 200 score to say that this model is good enough. And we're going to have a log, and this log is going to be our scores. And then we have our running average scores, just so we can store that and plot it after the fact is a little bit more helpful than the very noisy score results that we typically get. And so let's start playing games. For I in range num games, right? So how many games do we want to play? We're going to set our score 0, right? Okay, score 0 at the beginning of the game. And we're going to go ahead and start the game. State is equal to env.reset. Go ahead and start the game just like we always do. And done is false. And we'll do while not done. We're going to go ahead and select an action. Action is going to be agent dot select action at that state. And of course, at the beginning, right? At the beginning, our epsilon is set to 1. So the action we select will be completely random. But we're going to decay that as we update our model, as we take steps. So that's our action. And then we'll do our next state, reward, terminal, truncated, or blank, we don't really care about the extra info, is env.step action. So what I've done is I've taken a step with this action in this environment at this date, and that gives me my next date. What reward do I get is the game over, or truncated, like the game has gone on for too long, so the game itself like cuts off, says I'm done. And so our done will be if we died, right, fell or whatever, terminal, or truncated, right, if the game just went on for too long. We're going to do score plus equals reward. This is my current score up till now. And now that we've gone ahead and played a step, we want to store this memory in our experience tuple. So we're going to do agent.timecapsule.add_memory, and we're going to add in our state, next state, our action, the reward, and if the game's over. So this is me storing something. And then we're going to do an agent.trainStep batch size, right? So this is, again, me doing all of this. Go ahead and take a train step, updating our model. Now that we have all of this ready to go, and actually there's one small thing we forgot to add. When we grab a batch up here in our train step, if batch is none, return none, right? So if the batch is none, as in we don't have enough memories in our time capsule yet, then there's really nothing we can do. So we can just return none and just do none of this stuff. But once we have enough memories, then we can actually go ahead and start training the model. So there we go. That is our train step. And once we've trained the model, our state, right, the current state, is going to be the next state. And then we, again, repeat. We go ahead and select another action, and we just keep doing this over and over and over again. Once we've completed the game, right, so once it's done, right, so either our agent failed or the game went on for too long, our log scores dot append score, and then running average scores is going to be np.mean, and we'll look at our current list of all the scores for all the games we've been playing, and then just take the last, in this case 25 of them, but running average scores, take all of them, and just average them together, right? So this is going to be the average of my last 25 games. And we're going to store in our log running average scores dot append running average scores. And there we go. We can also print some stuff out if I % log frequency, right? So every once in a while, go ahead and print out, and I'll just copy this, right? The print statement, so it's easy. Go ahead and print out what game we're on, score, my average score up till now, and my epsilon. And then, of course, we have our ending condition, right? I mean, I've set it to play 500 games, but if it successfully beats the game 20 times before then there's no need to do all that. So we can do if scores, if my score is greater than my min reward, which we know is 200, to say that this was a successful game, we'll do ending tolerance plus equals 1. We've had one successful game. And we can do if ending tolerance is equal to the game tolerance, well, if in this case it's 10, so once I have once I've successfully done 10 consecutive games, then I can go ahead and break. Otherwise, if my score is not greater than the min reward, then I will start my ending tolerance back to 0, right, back to 0. So I need to win 10 successful consecutive games for me to say that that we have had a successful training run. And then we can, once all of this is done, so this will go ahead and break the loop if we're done, then we can go ahead and do a print, I don't know, like a completed training, and we can return our agent and the log. And so let's set the device to CUDA, if torch.CUDA is available, else CPU, that's fine. We know we have a GPU here, and we can do our agent, and log will be trainer with the environment, device equals device. So I'm going to leave everything else in the environment, everything else about our trainer, these defaults right here. That should be fine. So now to find out where our bugs are. All right. So first of all, expected all tensors to be on the device. Looks like something is not going on the device. Let's see here. So when we access memories, it's when we are running agent.trainStep DQN batch states. All right, let's check here. When I am grabbing access memories, this should have run it in device. Device equals device. Wait, let's just double check. My device actually is CUDA, right? Yeah, it is. Okay. So in that case, there's just something annoying happening. So let's check here first. Let's check up here, print batch states. Always get device errors. That's none for now, of course. So let's put this after right here. Here we go. So our batch states is sitting on the device, so that's good to see. All right, so what else could have gone wrong? Oh, let's check if our model's on the device first. That's probably it. So this should be .to self.device. Okay, good. Now we have our running average score, right? That shouldn't be running average score. First of all, running average steps right here. Running average steps. That'll compute the scores. All right, we have score is not true because there we go, it's plural. All right, there we go. We can see the game is now playing. And it looks like it's not working at all. All right, let's just try restarting real quick. Okay, it looks like our epsilon is actually not decaying. All right, so it looks like we have another bug right here. Let's do self.update epsilon. Self.epsilon print self.epsilon. Yeah, it looks like it's always 1, which is a little bit weird. So I guess I made a mistake here. Self.epsilon to the power self.epsilon decay. That seems, oh, of course, not to the power, it's times, it's exponentially decreasing. So we keep multiplying by it. Okay, there we go. Now we can see our epsilon is decreasing. So, we're no longer just randomly selecting stuff over and over again. And this will just go ahead and train. It takes a little bit of time. Of course, as the model gets better and better, games will take a little bit longer because it's not just crash landing, essentially. So we'll let this run, and I will come back once it's done. Okay, we have completed training, so we can see in 345 games, it has successfully reached at least 10 consecutive games. But there are a couple issues, but before we actually get into that, let's go ahead and just look at it. So here is just that same method from before. We're going to go ahead and play the game. We're going to inference our agent's going to inference from the state, go ahead and take that step in the action, and the game ends when the game ends, and we set the state to new state, and just play this game over and over again until we're done. And I go ahead and record it, and we can play the video right here. And we can see that, let's see, overall, it seems to be working pretty well, right? Maybe not perfect. We can try it a couple times. Here we go. Yeah, so there you go. We can set the seed or take the seed out, so it's completely random every time. In that case, it looks like it landed right there. We can try it again. In this case, it kind of seems to be always a little bit too far to the right, but that's fine. So that's a good start, but there are a couple of issues with what we had just done. This is probably easiest just to show with the plot. So let's just go ahead and plot our scores, and you're going to see it immediately. Look how noisy our scores are. Like sometimes you get these huge spikes going up and down. This is not very good, right? So this is a little bit of a problem because our neural network is struggling to optimize, and it gives us very noisy training regimes. And there's a specific reason for this, and that's our moving target problem. So there's something that we didn't implement that the original DQN does, and the reason for that is essentially this, and that's why I wanted to show you what we're missing. Whenever the moving target problem leads to something that essentially always looks like this, extremely noisy reward curves. And so let's kind of think about what the moving target problem is. Let's go up here to our training. The moving target problem is essentially the issue is that we have a Q network. Our Q network here is doing two different things. It's calculating the Q estimate for a current state action pair, and then it's computing the TD target by using the estimate of the Q value for the next state action pair. So that we did that right here. We're computing our Q estimate, right? Q estimates from our current states, right? For these states, but then we also use it to compute it for the next states. And our neural network's goal is to minimize the distance between this Q estimate and the computed TD targets, right? That's the main idea, right? We're using mean squared error to minimize the distance between the Q estimate and the TD target. But the problem is, again, the model is being used for both things. So by the time we've actually updated the Q model, the TD target has already changed, because our TD target will continue to change. It'll always keep changing every time we update the model. And so we're chasing down this TD target, but because it continues to change all the time, it leads to noisy, unstable training, right? And that's exactly what we're seeing here. We're essentially chasing down a moving target because our neural network continues to keep updating. And once we've updated, for the same input states, we'll end up with different values for that TD target. And so that's a little bit of an issue, and we need to deal with that. And the easiest way to deal with it is why not just use a static model. What we can do is create an exact copy of the Q model that we had before, but we're going to use that as a target model. And this Q target will just remain static for some number of steps, right? Just some number of steps. And then once we, once we've kind of completed those steps, then we can go ahead and copy the weights over from our actual Q model that's training to that one. So let's go ahead and see what that looks like. To do this, there's really not too many things we have to change. We need to just update our agent and the trainer. So let's go ahead and grab our agent here, and we're going to copy you down right here. So update our agent right here. Now let's just make the couple of changes that we need. So first of all, we still have the DQN like we did before, but now we're going to create a new one. We're going to create DQN next. So this is going to be self.dqn next. This is just going to be exactly the same model as before, right? It's just going to be the DQN model from before, but with two small things. First, self.dqn next, we're going to make sure load state dict, it has exactly the same parameters, right? Parameter values as the DQN, the original model. So we're going to take this model and we're going to initialize a new model and copy these weights into here so they're identical to each other. And then we're going to throw this model into self.dqn next.eval. Throw it into evaluation mode because we'll only ever use it in evaluation mode. So there we go. That is that. And again, it's exactly just two copies of the same model. One is just a duplicate of the other one. So that's all we really need to change up here. After that, during our train step, right? During our train step, what we have is our Q next estimate here is being computed with the same model. And what we want to do is use two separate models to do it. And so our Q next estimate won't come from DQN anymore. It's going to come from DQN next. And none of this is necessary anymore, right? We can get rid of all of that because it'll always be in evaluation mode. And this is going to help us solve our, essentially help us solve our target problem. Our TD target now comes from this thing, and this model is frozen. Our DQN model here will continue to keep updating. We're going to keep updating it over and over again, but although it's continuing to update, the target for it will stay the same. The target stays the same. So it's not changing as we're changing everything else. Otherwise, if the target keeps moving, then the model will optimize poorly, right? To avoid that moving target problem. But of course, we need to update this DQN model to, again, the DQN next model to be a copy of the DQN model every once in a while, right? So we just need to add that method in here as well. Def update target network self. And it's going to be self.dqn next dot, again, load state dict self.dqn dot state dict. Just like that. So I'm just going to go ahead and copy the weights of my DQN model into the DQN next model because I need to make sure that this stays, somewhat the same every now and then. And that goes ahead and updates our entire agent with the couple of small changes we needed. Similarly, we need to update our trainer. So let's go ahead and grab that. That will be down here. So our trainer will again be very close to what it already is, just with a couple extra steps. So first of all, we're going to throw another thing in here. We're going to do a update target frequency. And let's say it's 3. So we want to update our next model every 3 steps. So we're going to keep it the same for 3 steps and then copy everything in again. And so we just need to add that in. We will do if right here. First of all, we need our score. We'll also have our step equals 0, right? What step are we currently at? And throw that in there. And then we will have right here, after we've updated our model, right, train step batch size, we'll do if step percent or modulo update target frequency is 0. Then we'll do agent.update target network. And there we go. That's it. And we'll update or iterate step plus equals 1 right there. Nothing else should change as far as I remember. So let's try running this. So here are those final results. We got a model that in 125 steps ended up beating the game 10 consecutive times. So let's go ahead and just plot them just so we can see that. So let me go back up here. What we want to do is grab that plotting function so we can see the results. Well, we can actually play the game first. So let's do this right here. Let's play the game real quick. Let's call this stable. And then we'll replace you with that. So this is us playing this LunarLander game with our kind of slightly more stable model. Nice. So we can see it still made it, even though there's some randomness in the game where it pushes the lander around. We can try again. Looks like I made it that time. So yeah, good results. We're making it to the center, not so bad. And the more important part that we actually care about is how does our reward curve look? Because here we can see again, it was super noisy. But now, hopefully, looks a little bit better. And this looks quite a bit smoother. Obviously, we still see some big peaks and dips, but this still looks quite a bit better, mostly because we're able to optimize in just 120 iterations rather than the roughly 350-ish that we needed when we didn't have as stable of a setup. So this, again, points to why this is so important. Our DeepQ models need a solid target for us to minimize the distance between. The main takeaway should be essentially when we're training our model, if we are using the same model to compute the values or basically my Q values for my current states and also my target, every time I update my model, the targets change as well. And it doesn't give the model an opportunity to minimize that distance, because if the target keeps moving, then it becomes this moving target problem. It's just more unstable. So what if we could hold our targets constant just for a couple of steps, allow our DQN model to just optimize towards that constant just for a couple steps, and then replace my target model with my new model, my new DQN model, and then again optimize for a couple steps towards that constant target. Once I've taken a couple steps, again, repeat it. It just gives the model an opportunity to optimize towards a constant target rather than keep on changing. And this little change seems to help with training quite a bit, gives you much more stable overall rewards. So just again, the main change we did was go ahead and just create a copy of the network, an exact copy of the network. And instead of updating that copy all the time, like our DQN continues to change, just update it every now and then, right? And in our case, we're updating it every 3 iterations. So this is our first main deep dive into reinforcement learning. As you can see, there's a lot of really powerful ideas here, but they're all grounded in the same standard Q-learning methods. We're using the same TD function. Instead of using our Q update method here, we just reformulated it as just minimizing the distance between our Q values and the targets. Of course, there were the 2 extra additions. We had to train on batches, and we had to set our TD target model as constant for a little bit, just for better, smoother training. But this really sets us up for other value-based methods that we'll be looking at in the future, double deep Q learning and dueling deep Q learning. But the method we looked at here is crucial to kind of working up to those areas. So I will see y'all in the next one.